Welcome back to Geometry Classroom. Today we'll talk about segment lengths in a circle, intersecting chords, secants, and tangents. Our objective for this lesson is to apply the theorem related to intersecting chord, secant, and tangent to find the missing segment in a circle. But before getting into our lesson, let's recall a few things about chord, secant, and tangent. As we know, a chord is a segment whose endpoints are exactly on the circle. A secant is a line that intersects a circle in exactly 2 points, 2 different points. And a tangent is, again, a line that intersects the circle in exactly 1 point. Now, we have a few cases of intersecting segments in a circle. We have, in fact, 2 kinds of intersections. An interior intersection and exterior intersection. Now, when we talk about interior intersections, we have 2 chords intersecting in a point interior the circle, like in this case, right? So, chord AB intersecting chord CD at point E, which is interior. Now we have a theorem, right, that states if 2 chords intersect within a circle, like that picture, then the product of the lengths of the resulting parts of one chord is equal to the product of the lengths of the resulting parts of the second chord. In other words, after intersection, the resulting segments of chord AB are A and B. The resulting parts of the other chord, which is CD, are C and D. This theorem states A times B equals C times D, right? It's simple. Now, let's have an example. Find the value of x. Now, chord BD and chord AC intersecting at point E. The resulting parts of BD are x and 18, right? So, according to the theorem that we had previously, we multiply these parts, 18 times x. The resulting parts of the other chord are 12 and 9. Again, we multiply them. Now, that theorem that we had in the previous slide states these 2 products are equal. Then we simply solve for x. To solve for x, we divide by 18, right, both sides. And we get x equals 12 times 9 equals 108 over 18. 108 over 18 equals 6. That's the value of x. Now, another case of intersection between segments in a circle is when secants are intersecting at a point outside the circle, like here, we have here, or when a secant and a tangent intersecting, again, at a point that is outside the circle. When we have such cases, we have another theorem, yeah? Now, if 2 secant segments, right, 2 secant segments are drawn to a circle from an exterior point, A, right, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. Probably this statement is hard or difficult to understand. But if you look at the given picture, we will be able to understand much better. What does this statement says? The product of its external secant segment of one secant, which is A, right? Yes? And the length of the whole secant, which is A plus B, as we can see here, is equal to the product of the length of the external segment of the other secant, which is C, and the length of the other secant, which is C plus D. Yes? Now, let's have an example. In this example, it says if BC equals 6 centimeters, AD is 2 centimeters, AB is 4 centimeters, find X, which is the length of CD. As we know, according to the previous slide, that the product of the external segment of the first secant, which is AC, right, which is 4, right, times the length of the secant AC, which is 4 plus 6, right, equals the product of the external segment of the other secant, which is 2, times the length, the total length of the other secant, which is AE. And AE, as we can see, is the sum of this segment AD and segment DE, which is X. So inside the parentheses, we're going to write 2 plus X. Now we solve for X. But before solving for X, we have to simplify both sides, right? Now, first, we estimate or evaluate the parentheses on the left side. 4 plus 6 is 10. So we're going to have 4 times 10 equals. Now, we get rid of the parentheses there by applying distributive property of multiplication over addition. And we're going to have 2 times 2 is 4, plus 2 times x is 2x. Now, 4 times 10 equals 40, which is equal 4 plus 2x. Then we get rid of 4 by subtracting 4 on both sides. Yes, and we get 36 on the left side equals 2x. Then, to get x, we divide by 2 both sides, and we get 18 equals x. So that's the length of chord DE, which is x. Now, another case of intersection is when a tangent and a secant are intersecting at a point outside the circle. When we have such a case, the square of the length of the tangent, right, the square, equals the product of the length of the secant, right, which is D, and its exterior segment, which is B. Yeah? So we can say a square equals b times d. Good. Now, let's have an example. In the figure below, if AD, right, AD equals 9 centimeters and AC equals 25 centimeters, 5x. Now, according to the previous slide, the square of the length of the tangent, which is x squared, right, equals the product of the length of the secant, which is 25, and the length of its exterior segment, which is 9. Right? Now, we're going to have x squared equals 25 times 9 would be 225. Yeah? Now, to get x, we have to square root 225. So x would be square root of 225. But 225 is a perfect square, is the square of 15, right? So we're going to have square root of 15 squared, which is simply 15 centimeters. This is how we use theorems related to intersecting segments in a circle to find the missing segments. That's all we have for today. Thank you for watching my video. Next time we'll talk about equation of a circle. Thank you.